All right, we are on to module 11, I believe. Can't see. Graphs of functions. I know we got to make a decision about the test, but we'll see how long this takes and kind of go from there. But this is, of course, my pencil is not working. So graphs of functions. There are we kind of talked about this the other day for a second, but this is if you have a f of x, this always equals y, and this is like the point xy. So if the whatever's inside the parentheses is your x, and then whatever's it equals to is your y. So the biggest problem on this, or the biggest thing about this, is identifying which is your x and which is your y. So for A, it says h of 0. Find h of 0. This is saying x is 0. What is y? Why does my pencil stop working? That's awesome. Sorry, my pencil is not working. Are you kidding me? Man, let's try it again. Okay, f of x equals y. That's my xy. All right, so this is saying x is 0, what is y? So you go to x equals 0, which is, x equals 0 is right here at the origin. And at that point, when x is 0, my graph is at 2. So that would be my answer. The next one, though, says on B, it says h of x equals -2. So this one's saying when y is -2, what is my x? Okay, so that's kind of the big thing here is identifying when you're x and when you're y, what you're looking for. But if you're inside the parentheses, it's your x, and then if it's equal to, that's your y. So this one, we go to when y is -2. So when y is -2, it's actually right here. So you could use the point -1, -2, or you could use the point 2, -2. It just says find one value. So you could use either one of those. Okay. So a lot of times on the y one, there is multiple values that x could be, but Alex just tells you to find one value. All right, the domain and range. So we've talked about the domain and range a little bit with equations, but when you're looking at graphs, the domain is your first one, your first element, which we associate with our x's, and our range is our second one, which we associate with y. So our domain, like if we on this one, it just says points. So the 3 points we have are -3, 3, -3, -4, and 2, 3. So my domain is a set of numbers. It's a set of x's, so you do use the brackets, and you would say, okay, the set of my domain is my x's. It is -3. You don't have to write -3 twice, so -3 and 2. And my range would be the set of y's. That would be 3 and -4. You do not have to write 3 twice, okay? So your domain is every number on the graph that can be an x, and the range is every number that can be a y. So on this one, it's just a point, so it's not bad. On the next one, it does get a little tricky. So same idea on this one, but we have to be careful on this one because our x's and our y's, so there's a lot more x's and a lot more y's. You are going to probably have to write this in interval notation. So the way you think about this one, our domain is our x's, right? And the x-axis runs left to right. So what you want to do is you want to write this from left to right. How far left it goes to how far right it goes. The furthest point left on this graph is right here at -4. It is going to be a bracket at -4 because it does equal, right? Because you have the solid dot. And then the furthest point right of this graph is 1, and it's going to be a parentheses because it is an open circle. Okay, so since that is an open circle, you would just use a parentheses. So the left to right, the domain doesn't usually mess with you too bad, but it's how far left the graph goes to how far right it goes. And this is kind of weird the way I say the range, but it's the same idea, but the range is vertical and it deals with the y's. So it's how far down it is to how far up, down to up. I know that's kind of strange to say, but you want where's the bottom of this graph to the top of the graph. So the bottom of the graph is at -5, and it does equal -5. And the top of this graph is at 4 with an open circle, so it's going to be a parentheses. So you do a bracket where it equals or a solid dot, and you do a parentheses when it's an open circle or when it's infinity. But this is, the range is left to right. The domain is your x's, so it's left to right. Your range is your y, so it's the bottom to the top. How far down it goes to how far up it goes. This is something that is useful, like if you're talking about like manufacturing, like how many products can you manufacture a day and still make money versus how much the factory can actually manufacture, and different things like that. I was trying to see a different shape here. Let's see if I get one. Yeah, we can do that one real quick. All right, so on this one, again, my domain is my x's, so I'm looking left to right. So the left point would be -4, it's a parentheses. And the right point would be 5 with the parentheses because they are open circles. The lowest point on this graph, the lowest point is at -2 with the parentheses, and the highest point is right here at 4 with the parentheses. Okay. So the range, Apple has tried to correct my handwriting and make it look better, and that's not good. So it's down to up, and the domain is left to right. All right. So the next section, the next module is all about transformations, and so we'll talk a lot more about that next time. Why is this one in this section? They moved it for a reason. I bet I can't move it back. All right, so I'm gonna I was really waiting the next section to talk about this. I was trying to think of a different way to do this for now. So every quadratic equation, they call it the parent function, it starts with x squared. Okay, so like the graph shown that they give us right now is x squared. When you start adding, subtracting, multiplying, and doing different things to it, it changes the shape of it. So, trying to write here, x. This is the vertex formula. I think we've seen that before, last section. But the way that we'll talk more about this in the next section. I was trying to think of an easier way to do this. Basically, the way that I think about this is between inside and outside. All these work the same way. And the thing is, we can do these transformations with absolute value or x cubed. They all kind of work the same way. So the way I split it up is if you do something on the outside, it's going to do something vertically. Okay? So in this scenario, it's going to go up or down. So when I have x squared and I subtract 3 on the outside, that is going to move it down 3. So it just takes this graph right here and moves it down 3 spots and has the same graph. Alex does this pretty easy for you. I believe like you just use this function right here and you just move it. So you don't have to like plot a bunch of points. You're just taking the graph and moving it. Okay. So the outside is pretty easy. The outside is definitely the easiest one where you move it. You add or subtract the number on the outside. What I mean by the outside is that's not being squared. Okay. If I look at this one, this I would call the inside. The inside always does something horizontally. So if you are inside the part that's being squared, or if you're inside the absolute value, or if you're inside the square root, it's going to move it left or right. The problem with the inside is you always think opposite. Okay? So if I told you this -5 right here, your first thought is probably that it moves it to the, if it moves it left and right, your first thought is probably that it moves it to the left 5. But if I look right here, my formula starts with a negative in it. So the only thing I'm really looking at is the 5, which makes it positive. We'll talk more about that. But you always think opposite. Like I think x -5 would move it to the left, but it actually moves it to the right 5. So I take this point right here and move it to the right 5, and my graph should be look like that. We'll definitely do more of that on Thursday, if not a little bit today. We'll see how fast we'll get through these. So just to do another one real quick to see how Alex works. So the first one is x plus 4 squared. So that's going to do the opposite of what I think. It's on the inside, so it moves it left to right. It's actually going to move it to the left 4. And all you got to do, you see how I did that on Alex. You just click that button right there, and then you can move it up or down, left or right. So that plus 4 actually moves it to the left 4. The x squared minus 1, the outside's easy. It moves it up or down. Minus 1 would move it down, down 1. Okay. So you, outside always messes with it vertically, and the inside always messes with it horizontally. And when you do something on the inside, it's always like the opposite of what you think. Just going to write this real quick here. This would be left 4, and then this one would be down 1. All right, increasing, decreasing, and constant. So a graph is always one of these three. It is increasing, decreasing, or constant. That means it, like if it's increasing, you always, okay, so the key to this is always looking left to right, because we read left to right, so we always look left to right. If it's going down, it's decreasing. If it's going up, it's increasing. If it's staying flat, it's constant. So from A to B is going down, right? So that would be decreasing. Okay. From B to C, it's going up. So that would be increasing. From C to D, it is going down. So that would be decreasing. And then from D to E, it's going flat, so it's constant. Okay. So identifying those isn't bad. But every time there's a turning point, like each of those little vertices right there, I call them turning points. They use that language in pre-calculus, I think. But the turning points, it could change direction of whether it's going, it's increasing or decreasing or constant. So that one's not bad where they just give you the multiple choice. Oh, I accidentally put that one in the wrong spot. Okay, I'll fix that later. Interval notation. So when you move to like the interval notation one, sorry, I got to like work every problem from Alex because we're all talking about graphs. So, there's a lot. Oh, wait, did I get a weird one to start? I did. Let's try another. That answer was none. Okay. So the trick to this one is you got to write an interval notation. But the trick to this is we are looking from left to right. Okay. So since we are looking left to right, you want to make sure you always use your X's. Okay. You do not want to use your Y's. The thought process here is I don't care how much it's increasing or decreasing. I just want to know where it is decreasing. So the key word here is where. Anytime you use where, you use your X's. X tells you where to find it, and Y tells you how much it's changing. So you're always use your X values here. So we want, on this one, we only want decreasing, okay? So let's go find our decreasing. Decreasing from here and here are my only two decreasing, right? So look at your X. You want to know where it is decreasing, not how much it is decreasing. So it starts decreasing right here at -2, and then it ends decreasing right here at 0. And then our next decreasing spot is 4, and it decreases until it gets to 5, okay? So you use your X values. You always use parentheses. For these, you always use parentheses. All right, parentheses. You always use parentheses on these because a bracket means that it equals, and when you're standing still, you're not increasing or decreasing or anything. So you always want to use a parentheses on these. So read the problem because you do only have to find. My goodness, I hate every time it does that. You do only have to find like whether it's increasing or decreasing or constant. You do not have to find all of them. This was like the first one I got just to like tell you, but this one says when it's increasing, well, this graph is never increasing. It's always decreasing or constant. It goes decreasing, constant, decreasing, constant. Okay. So it can't possibly be there. None of them. All right, we'll do one more of these just to make sure. Okay, so this one, what's it want? It wants increasing. So that would be this one and this one. So we go from -6 to -4. Again, I do not care how much it's increasing. I just want to know where it's increasing. So I always use my X values. And then 1, 2, 5. Okay. Always use your X values and always use parentheses on these. You want to know where it's increasing, not how much it's increasing. Finding a domain and range linear graph in context. All right, this one. Heather wanted to study the area of a rectangle changes with the length and the width changes with the length if its width is fixed. She computed the areas of several rectangles that have the same width and different lengths, and she plotted this graph below. So my domain on this one, we don't have to use interval notation, it doesn't look like. It says write your answer using inequalities. Nothing's going to change here in the way we're doing. Domain is going to be my X values. I'm looking how far left to right it goes. So my domain goes from 0 to, and it has an arrow, so that means it keeps going. So this is going to be X is always greater than or equal to 0. And my range is going to be my Y's, and it's going to be how far the bottom of the graph is to how far the top of it is. So the bottom of this graph is at 0, and again, you have the arrow. So it is going to go up as it goes, right? So this is y is greater than or equal to 0. A lot of times in context, your answer is going to be like greater than or equal to 0 because like I used a manufacturing concept earlier, and like you can't manufacture a negative amount of goods. Like you can manufacture 0 or more per day. You can't, I was going to say make money, but I guess you could. And you can't work that many hours. You can't, a lot of times it is 0 or more because you can't have a lot of negative numbers in context like that. All right. Local minimum and maximum. Hold on real quick, sorry. I want to make sure I wrote the answer right on this one. I'll leave the answer in there, that's fine. Okay, so local minimum and maximum. So we have two different types of local minimum and maximum. You have local and you have absolute. So the first one is local. What this does is if I looked at the lowest point of this graph, the lowest point of this graph would be negative infinity because it goes on forever, right? And the highest point of this graph would be infinity because it goes up forever. So if I ask you the minimum and maximum of this graph, it's not very useful to be negative infinity to infinity. We're talking context here, I can't think of an example of this one that's decreasing like this, but I want to know what makes these changes. Like, what are making these changes right in this area right here? So, like, this is what it means by local. Like, what causes this? What could be my highest point and my lowest point in these? So what the local does is it kind of ignores the negative infinity to infinity, and you find the lowest there. So the local maximums are kind of the highest points in general. So it's kind of like where you have peaks, I guess to say. So my local maximum would be this point right here, which is what? -2, 3. But it would also be this point right here because that's like a maximum. So maybe you're talking about like, I'm stuck on kind of the finance and manufacturing, but like quarters. Like you want your maximum in the first quarter and you want your maximum in the second quarter. So you have two different maximums. Now, I told you a second ago that X is like the location, the where, the location or where, and then Y is what it actually is. Like how much it's increasing, and different things like that. So you have to be careful with your wording here because oh, it switched it on me. They switched it on you. That's why you got to be careful. I'm going to look at the bottom one first. All values at which X has a local maximum. This is telling you at. This is telling you where. Okay, so this is always your X values. The way that I learned it is at X and it is Y. It's at X tells me where to find it. Okay, so all the values of it where at which F has a local maximum, these are my X values. Okay, so these are my X values. My Y values are what they actually are, all local maximum values of F. So these are what the maximum values actually are 3 and -1. Okay, so that's where they get those numbers. The hard part is trying to figure out where the X and the Y are, but X tells you it's at X, and then Y tells you what the actual maximum or minimum is. And it confused me there for a second because it does switch those on you. I'm like all off on my topics here. I'll go back and fix it, but let me try to get right. Okay. Let's do another one of those just to make sure. I wanted to do one where they switched it on us. This one. Okay, not all of them will have two peaks like that. You could have one like one right here. And make sure you pay attention to whether you're finding the maximum or the minimum. So this one we are finding the maximum, right? Okay. So we're only looking kind of generally right here. We're ignoring the to infinity and to negative infinity and looking at our peaks here. So this is at the point 2, 1. So if it's at x and is y, it's going to be at 2, and my maximum value is 1. So 2 tells me where to find it, and then 1 is actually what it is. So all values at which g is at would be my x, and the maximum value actually is 1. Okay? So that's the hard part, is identifying which answer goes where. But again, x tells you where, y tells you what it actually is. I'm going to solve this just to make sure, because all right, when you switch to the absolute maximum or minimum, you try not to ignore the infinity as much, because it's absolute. Okay, so when you see the word absolute, it is a little bit different. Did my pen stop working again? No, just... Okay, so the absolute's a little bit different. So what we look at here, the absolute maximum of g. So if I look at where this graph goes, this would be the local, right? Because that's the highest point, ignoring the infinity. But since this goes to infinity, there actually is no maximum, because there is no end that it could have since it goes to infinity. So it is recognizing that there is an infinity when you do absolute. Absolute kind of looks at the whole graph, and local just looks at those little peaks and valleys, the humps and peaks and things like that, okay? The minimum, the lowest point of this graph would be right here, right? And it is -4. On the other one, my maximum is the highest one, which is 3. And my minimum would be right here at -5. Okay. So again, on this absolute one, we didn't use this one, okay? So when we look at local, we want, okay, here's a peak, so those are both local. But the absolute just wants the highest point, or just wants the lowest point. That's kind of the difference. Absolute's the whole thing, whereas local, we look at every peak and every valley. So like this one would be a maximum, a local maximum, a local maximum. This would be a local minimum, a local minimum, a local minimum. But the absolute, we only pay attention to the highest one and the lowest one. And when it goes to infinity, we actually say none, because there's no cap. Like you could keep going as much as you want. Oh, what's this one? Oh yeah, this one's not bad. So this one is just recognizing when the graph is positive, when the graph is negative, when it crosses an axis. So the first thing is just like the first problem we did. When you have f of 4, that's saying x is 4, what is y? So you go to x equals 4, which is right here, and my y is 3, okay? And it's saying, is that positive or negative? Well, no, it's positive, right? It's positive 3. So you don't really have to do all that work, but you want to identify whether it's above the x-axis or below. So you're talking about money. If you're above the x-axis, you're making money. If you're below the x-axis, you're losing money. So you want to, like identifying positive and negative is good. Okay, find which values f of x equals 0. So equals 0 would be like it could be a break-even point, or, you know, if you're throwing a ball or something, is when it hits the ground. So this is saying, what is x when y equals 0? So we look all across when y equals 0. Oh, this is the y-axis. It is usually, if it's in between right there, it's probably going to be, like just do half and it should count it right. This is the y-axis. So we're actually finding the y-intercept here, so this isn't like the ball hitting the ground. This would be like, I'm struggling coming up with ideas at 8 a.m. So this is finding the y-intercept is what that actually is. I'm sorry. Did I do that backwards? I'm losing my mind. When y equals 0, it is the x-intercept. Why did I talk myself out of that? It is finding, yeah, when y equals 0, you find the x-intercept. My goodness, sorry. So the x-intercept, okay. It is like the ball hitting the ground. I should have stuck with my initial thing. It would be like the ball hitting the ground, like, woo, you throw a ball, it hits the ground, and you want to identify your x-intercepts. Okay. Y equals 0 gives you the x-intercept, so it is 3 right here. The answer is 3. My bad. I was kind of surprised I gave you a fraction there. Whew, losing. Okay. All right. Next one, for which values of f of x is less than 0? What this is saying is when is the graph negative? When is the graph negative? Okay. So it is negative. Write your answer in interval notation. It is negative from -5 all the way until 3. You would use a parentheses because when it equals 3, it is actually equal to 0, and we just want less than 0. At 3, x, why did I do that? At 3, x equals 0. And we only want less than 0. So that one kind of just puts together some of the different stuff, but the positive and negative and identifying when a graph is there is useful in real life context. All right, choosing a graph to best fit the narrative. This one shouldn't be bad, but I've been trying to come up with examples on my own. This one kind of shows you the difference between constant, increasing, decreasing in those. Rita walks at a constant speed to the store. So that would be, keyword there is constant, obviously. It would be something like this, where the graph is flat. Karen climbs up a ladder to the roof. So if we are looking at her distance above the ground, as she goes up the ladder, she is getting further from the ground. So the distance from the ground would be increasing as you go up a ladder. Okay. All right, so this is being able to look at a or a function and being able to see kind of what's happening with the graph. This is our whole goal on Thursday too, but choosing the description for h of x equals 2x squared minus 1. So 2x squared, as soon as you see x squared, you know it's a parabola. So that's the first thing to identify. So that narrows out like 4 of the options. Remember, if the number in front, which we call a, if a is positive, it opens up. So this one would be this right here. This one kind of looks like y equals mx plus b. So we're talking about my m, the number in front of x. My m is 4, so that is positive, right? So if it's positive, it should have a positive slope. So a line with a positive slope. And the last one, this is like y equals 1. When it's y equals a number, it is a horizontal line. So what we're going to be able to do is start looking at the functions and the equations and be able to identify what's happening with the graph or kind of a general idea of what it looks like. Horizontal line test. So last week we talked about the vertical line test. The vertical line test said if you draw a line, a vertical line anywhere on the graph, and it hits it more than once, it is not a function. Okay, the horizontal line test, guess I need to write this out real quick. The The horizontal line test does the same thing, but horizontally, and what it's talking about is a one-to-one function. To be a one-to-one function, so y'all remember to be a function, what the definition was is for every x, there is exactly one y. For a one-to-one function, it says for every x, there is how do I say this quickly? There's a way to say this quickly and I can't think of it. It's both. There's got to be a way to say for every x there's exactly one y, and for every y there's exactly one x. Okay, it goes both ways. For every x there's exactly one y, and for every y there's exactly one x. Sorry, I don't want to write all that out, but it goes both ways. There's exactly one. They are one-to-one. There's exactly one x for every y. There's exactly one y for every x. Okay, so if you draw a horizontal line on these, we'll talk a lot. Well, we'll talk more about one-to-ones later on. But if you draw a horizontal line anywhere on there and it hits it more than once, it is not one-to-one. These are all separate, aren't they? So that would be this one. When I draw a horizontal, it hits it twice, so that is no. Are these all good? That is no. This one would be no because, like, right there, it hits it twice. Wait, this one was yes, wasn't it? I never hit two of them, did I? If it hits it twice, it is not one-to-one. That means it could still be a function, but maybe for a y, every y, there's exactly one x. There's two x's on that one. So, like, a y -4 right here, I get 2 and -4. That makes it not a one-to-one function. Okay, so horizontals, just like the vertical line test, is just determining if a function is one-to-one. So vertical determines if it's a function. Horizontal determines if it's a one-to-one function. We'll talk more about inverses as we go throughout the class, but in order for a function to have an inverse, they have to be a one-to-one. That's kind of why we start with that. So in order for you to have an inverse, it has to be one-to-one. So let's write a couple inverse facts here. To have an inverse, the function has to be one-to-one. Okay, that's like the first thing. That's why we check that horizontal line test. Inverse graphs are symmetric across y equals x. So when we get done with this, our graph will be symmetric across that line right there. Okay, it'll flip over. Now, this is actually super easy to do this. The way you want to do this is find every vertex point, find every turning point, and write down those lines. Or those points, I mean. -8, -7, 0, -6, and 5, -3. To find the inverse, I'm going to want this area right here. To find inverse, you switch the x and the y. So it's super easy. You just write a couple points, all the turning points, and then you just switch the x and the y. So this becomes -7, -8. This becomes -6, 0. And this becomes -3, 5. Okay? So this is, they write f to the -1. That f to the -1, what it looks like, that means the inverse. So my F is those ones, and then to switch it, you just flip the points. So now if I go graph this, -7, -8 would be right here. 0 or -6, 0 would be right here. And what's the other one? -3, +5 would be up here. So if I draw that out, you can see it becomes symmetric across that y equals x. So all you have to do to graph an inverse is find a couple points on it, find the vertices, and flip the x and the y, and it will make the graph for you. All right, that took a little longer than I thought, so we're definitely not going to the next section today. But that's fine because